Friends, welcome to my channel. Dhanesh here. In this video, I am going to discuss about bracket notation or Dirac notation. It is one of the most important concepts in quantum mechanics and quantum computing. Bracket notation is a standard notation for describing quantum states in the theory of quantum mechanics composed of angle brackets and vertical bars. It's introduced by Paul Dirac. Paul Dirac was an English theoretical physicist who is regarded as one of the most significant physicists of the 20th century. Dirac made fundamental contributions to the early development of both quantum mechanics and quantum electrodynamics. Let us discuss some aspects of vectors. Here I, j, k are unit vectors along x, y and z axis. I can be written as 1, 0, 0, j, 0, 1, 0, k, 0, 0, 1. We will discuss about Dirac notation of kets, that is the ket vector. See, ket vector is an abstract entity and serves to describe the state of the quantum system. We say that a physical system is in quantum state where represents some physical quantity such as momentum, spin, etc. when represented by the ket. We'll discuss on Dirac notation of bras. To get the bras from the ket, you need to do two operations. One is you need to transpose the vector, and after that you need to take the complex conjugate. Let's say z is equal to x plus jy is the complex number where j is equal to root of -1. You are familiar with that. Then the complex conjugate of that complex number is z bar. We will call it as z bar is equal to x minus jy. If it is 3 plus 2j, the complex conjugate is 3 minus 2j. Simple. So to get the bras from the kets, you need to do two operations. You need to transpose the vector, and after that you need to take the complex conjugate. This is called the Hermitian conjugate and is denoted with a dagger. Here the star represents the conjugate. Here you can see it here. The Hermitian conjugate is denoted with a dagger and it is known as the bra vector. The representation of bra vector, first it is written as with a dagger. After that it is with a angled bracket and a vertical line. It's a vertical bar and an angled bracket. Brackets, it contains both the bra vector and the kets. Bras and kets can also be written together to signify an inner product. Inner product means scalar product or dot product of the vectors. You know that A dot B is equal to AB cos theta. This multiplication, we call it as the inner product or dot product. The inner product, as we discussed, is a generalization of the dot product considering the original vector in three-dimensional space. If we want to denote the dot product using Dirac notation between this vector and its Hermitian product, we can combine our bra and kets as x square plus y square plus ez square. So this is the brackets notation. Brackets notation is also known as the inner product or dot product. Brackets is the inner product of Bra and Kets, Bra vector and Ket vector. So you may be familiar, Z is equal to X plus JY, Z bar is equal to X minus JY. Then multiplying Z is the complex number and Z bar is the complex conjugate. When you multiply a complex number with its conjugate, you will get x square plus y square. Here you are applying just a plus b into a minus b. A plus b into a minus b is a square minus b square. Here, j square will come, so that's why this becomes plus. On qubit notation in terms of brackets, brass and ket vectors. Classical bits always have a completely well-defined state. They are either 0 or 1 at every point during a computation. There is no more detail we can add to the state of a bit than this. So to write down the state of a classical bit, we can just use these two binary values. This restriction is lifted for quantum bits. Whether we get a 0 or a 1 from a qubit only needs to be well defined when a measurement is made to extract an output. At that point, it must commit to one of these 2 points. At all other times, its state will be something more complex than can be captured by a simple binary value. To see how to describe these, we can first focus on the two simplest cases as we saw in the last video. It is possible to prepare a qubit in a state for which it definitely gives the outcome 0 when measured. We need a name for this state. Let us be unimaginative and call it 0. Similarly, there exists a qubit state that is certain to output a 1. We shall call this 1. These two states are completely mutually exclusive. Either the qubit definitely output as a 0 or definitely output as a 1. There is no overlap. One way to represent this with mathematics is to use two orthogonal vectors. That's the brass and the kets. That's what I have shown it here. Let us explore the qubit by using qiskit. For the installation and configuration of the qiskit, please watch my previous video. Let's start. First, we need to import all the tools that it is needed. Let me do that. Let me run this. So I have imported quantum circuit and plot underscore histogram kit. We use the quantum circuit object to store our circuits. This is essentially a list of the quantum operation on our circuit and the qubits they are applied to. Quantum circuits, our qubits always starts out in the state 0. It's the ket 0, ket vector. We are taking, it's a vertical bar and a bracket. So it starts with the state 0. We can use the initialize method to transform this state into any state. We give initialize the vector we want in the form of a list and tell it which qubits we want to initialize in this state. Let me run this. Yeah. So you can see it here. The output, you can see it here. I just created a quantum circuit with 1 qubit and I have defined the initial state as ket 1. So you can see the ket vector, it is initialized to 1. Then I have used the initialize method. So I have applied the initialization operation to the 0th qubit, and I have drawn the circuit. We can use one of qiskit's simulators to view the resulting state of our qubit. To begin with, we will use the state vector simulator, but we will explain the different simulators and their use in the coming videos. Let's do it now. The state vector simulator of the qiskit. So this will tell the qiskit how to simulate our circuit. Let me run this piece of code. So it's working fine. To get the results from our circuit, we can use execute to run our circuit, giving the circuit and the backend as arguments. We then use the result method to get the result of this. So I have created the quantum circuit with 1 qubit. After that, I have defined the initial state as 1 using the ket vector. Then I have applied the initialization operation to the 0th qubit. Then I have do the simulation and it is returning the result. From the result, we can get the final state vector using dot get underscore state vector. To understand more clarity on state vector, you can watch my previous video related to state vector. Let me run this piece of script. As you can see here, you can see the output. So I have created again a quantum circuit. After that, initialize the state, and I have initialized the 0th qubit. Then I am displaying the output state vector here. So Python uses J to represent the complex number. J is equal to root of -1. In math, sometimes we use I as complex number, but in Python, here we are using J as the complex number. Its value is root of -1. We see a vector with two complex elements, 0, and you can see it as 0j. There you have the real part and the imaginary part. So you have 0 plus 0j and 1 plus 0j. Let's now measure our qubit as we would in a real quantum computer and see the result. You can see the output here. So this is the output. You can see it here. Instead of the state vector, we will get the counts for the 0 and 1 result using the count method, get underscore count method. You can see the output as the histogram output. You can see it here. We can see that we have 100% chance of measuring 1. This time, let's instead put our qubit into a superposition and see what happens. We will use the state Q0 from earlier. So here you can see the 100% chance. Let me run this. So here we will use the state Q0 as 1 by root 2 0 and I by root 2 1. So we need to add these amplitudes to Python list. To add the complex amplitude, we use the complex giving real and imaginary parts as arguments. You know that a complex number is having a real part and imaginary part, that you know in math you might have learned it. Then we repeat these steps for initializing the qubit as before. Let me run this. You can see the output. Now we will see the histogram output. You can see it here. This is the output from the histogram. So we can see we have equal probability of measuring either the ket vector 0 or 1. To explain this, we need to, to understand this, you need to understand about measurement. So the rules of measurement, you need to understand how this happened. So that we will discuss in the coming video. Thanks for watching. Please like, share and subscribe. Thanks a lot.